Good afternoon everyone. I am Chanda Devnath, one of the PMRF fellows of ISER Badhampur. I am the TA of this course Reagents in Organic Synthesis, instructed by Professor Subhash Chandra Pan from IIT Guwahati. In these classes I usually discuss about the questions based on this chapter, that is Reagents in Organic Synthesis, and I also try to discuss some concept before discussing those questions, which may help you to understand or to attempt your assignments and also the upcoming examinations like the CSI NET and GATE. And whatever questions I have taken, they are mostly from the different important books or previous year NET or GATE examinations. So let's start. In the last classes, I have in the last videos, if you have checked, I have already discussed about oxidation, reductions, or oxidizing reagents, reducing reagent. Then I have discussed about some non-transition metal reagents, some reagents for hydrogenation, and some transition metal reagents also. So today I am continuing the transition metal reagents containing the transition metals. So let's start. So there are various reagents containing transition metals like titanium, ruthenium, palladium, copper, chromium, manganese, zinc, rhodium, iridium and nickel. So among them, in the last class I have already discussed about titanium, and I have discussed about titanium. So today I will discuss some of these metals like ruthenium. Today I will discuss about ruthenium, palladium, copper and some bit about cobalt and iron also, and some bit about cobalt and iron. Okay, so let's start. So most of you have listened, like I have gone through, like palladium is one of the important transition metal among the inorganic synthesis, because there are various kind of reagents or there is various kind of catalyst of palladium which can be used in a various way to get our desired product. So palladium is one of the important type of reaction. Palladium catalyzed one of the important type of reaction is carbon-carbon cross-coupling reaction, by which we can form a carbon-carbon bond between two different moiety, like it can be intermolecular or intramolecular. You can form a carbon-carbon bond. You know that forming a carbon-carbon bond is one of the challenging process in organic chemistry because of their similar electronegativity and all. The bond is the formation of this type of bond is bit difficult. So the palladium catalyzed cross-coupling reaction are class of highly successful reactions with application in organic synthesis to have emerged recently. So to form any biological compounds, suppose any medicinal compounds or anything, all organic compounds are made of carbon and hydrogen mainly. Oxygen, nitrogens are also there, but mainly the core structure is carbon and hydrogen. That's why they are called hydrocarbon and all. So to form that a new bond between two carbon, sometimes if it is single bond, it's bit easy to form a single bond between two carbon atom. But when there is a carbon atom formation of carbon bond between two sp2 bond or two sp3 bond, that's the sp bond is sometimes a bit difficult. In those cases we need a catalyst to form that carbon-carbon bond. So the reaction carry out a coupling of aryl, vinyl or alkyl halide substrates with different organometallic nucleophiles, and as such it encompasses a family of carbon-carbon cross-coupling reactions that are dependent on the nature of the nucleophile. So the nucleophile can be different. If it is boron, then it's specifically named as Suzuki coupling. If it is tin, That is called stele coupling. If it is silicon, that is Hiyama coupling. If it is zinc, this Negisi coupling. And if it is magnesium, this is called a Kumada coupling. So there is a, here I have shown in a shorter way all the different type of coupling. First one is Suzuki coupling. Where is it? In case of Suzuki coupling, the nucleophile is boron. So here you can see, here there is a nucleophile boron. In this case, there is a alkyl halide. The halide and the boron gets removed from the system, and aryl and R get form a carbon-carbon bond between them. This is called a cross-coupling reaction. Next is stele coupling, which containing tin as a nucleophile to resulting a same kind of product. So the next one is Heck coupling, where there is no such nucleophile is used. There is only a carbon-carbon bond is formed. Next is Hiyama coupling, using silicon as a nucleophile, Kumada using magnesium, and Negisi as a zinc. Okay, so there are different type of coupling reactions. So all this has a in general mechanism where this palladium undergoes the oxidative addition between this carbon halogen bond of this. After that, it undergoes a 1:1 addition. It undergoes a nucleophilic substitution with the nucleophile. This nucleophile goes to the R group, and X removes with E, and through reductive elimination we get our desired product. There is another use of palladium catalyst that is called, other than like carbon-carbon cross-coupling reaction, that is called Suji-Trost reaction. In this case, the Suji-Trost reaction is a palladium catalyzed substitution reaction involving substrate that contains a leaving group in an allylic position. So in this case, there is a leaving group at the allylic position of the double bond. In presence of palladium, this leaving group gets removed from the system, and it forms a pi-allyl complex with palladium. After that, nucleophile adds, and it forms this substituted product. But there are some drawbacks, because in this case you always need a leaving group to form this allylated product. There are some alternative also for this reaction. This is a huge application of this Suji-Trost reaction in our in our organic synthesis and industrial chemistries also. There are some alternatives of this Suji-Trost reaction where we can eliminate the use of requirement of the leaving group, where that is called allylic CH oxidation, and another is propargylic CH activation. So that will be propargylic CH activation. So what is called allylic CH oxidation? First talk about that one. If there is a allylic CH, and if you add palladium and any oxidant into it, this allylic CH it's removed through oxidation, and it form a similar pi-allyl species. There is another alternative that is called propargylic CH activation. In this case, this type of CH bond, which is adjacent to this alkyne, undergoes a activation in presence of palladium or any Bronsted acid to form this type of pi-allyl species. And when you add nucleophile into it, you give the similar product as we get in case of Suji-Trost reaction. Okay, so these are some important concepts for palladium catalysis. So let's solve some questions. There are various type of examples and questions based on this, which we will discuss after that. Then another type of use of palladium is in hydrogenation. So catalytic hydrogenation of alkene. Alkene are treated with hydrogen gas in presence of metal catalyst such as palladium carbon undergoes the addition of hydrogen. So if there is a double bond, if there is alkene and you perform this hydrogenation, you can get alkene from this by this. So addition of hydrogen, and the specific factor of this type of hydrogenation is it will be always a seen hydrogenation. It will be stereoselective and it is always a seen addition. Always a seen addition. Okay. So instead of palladium, we can also use platinum, platinum O2, palladium hydroxide, and also rhodium and nickel. Okay. So alkenes can generally be hydrogenated in presence of many other functional groups except alkynes, which are more reactive. So if there is any such other functional group like carbonyl or benzene ring, alkene specifically reacts faster than that of the other functional group. But if there is alkyne, suppose this type of compound is there, a combination of alkene and alkyne, and you perform the same type of reaction. In that case, the alkyne get hydrogenated at the faster rate than that of the alkene. Okay. Other functional groups such as NO2, CN, carbonyl, and others can undergo catalytic hydrogenation with appropriate choice of catalyst. With the appropriate choice of catalyst and hydrogen gas. So let's let's solve some questions based on this. So the major product form in the given reaction is. So they have asked for the major product form in the given reaction in presence of PDP-4 acetic acid and 75-degree temperature. So what will be the major product form in this reaction? I just give 1 second, 2 seconds, just try. Okay. So you know about the Sooji-Trost reaction. I just discussed about the Sooji-Trost reaction. So what for a recap of again, if there is a leaving group adjacent to an alkene, then it can, in presence of palladium, This eliminates from the system and it forms a parallel complex with the palladium. A nucleophile can, if you add a nucleophile into this, we attack and we get our substituted product. Okay, so here where is the nucleophile? Here OAC can be considered as a living group. OAC can be considered as a living group. So in presence of palladium, it can be eliminated from the system, forming a parallel species. Forming a parallel species. After that, there is an internal nucleophile. Alkene is there, so alkene can act as a nucleophile. As alkene is there, so alkene can act as a nucleophile. So it will attack to this parallel complex as a nucleophile. So now the question is, it will approach from the above the plane or below the plane, because stereochemistry is a matter of concern, because in the product they have shown a specific stereochemistry of these two hydrogen, which means you have to know how the carbon-carbon bond will form. It will form above the plane or from the below the plane. Now this total part of this compound is above the plane because it is attached with this above the plane side. So this alkene is presenting above the plane of this carbon-carbon bond. So this will approach from the same plane. So it will approach from the above the plane. To this parallel complex, and then it will form this type of 5-member ring. This type of 5-member ring. Now there will be a positive charge. Now there is already a proton is available here. So it undergoes elimination. So the correct option will be, so as these two bonds are above the plane, so these hydrogens will be, both the hydrogens will be below the plane. So it will be a 5-member ring with hydrogens below the plane. So and alkene, exocyclic double bond and exocyclic double bond. So correct option is option A. The correct option is option A. Understood? Let's go to the next question. So the major product form in the following reaction is. So they have asked for the major product form in the following reaction. So this is one of the another feature of palladium, which I just discussed. So this parallel species can be formed in 3 ways. Parallel species can be formed in 3 ways. One is by using a living group. Second is through allylic CH oxidation, where we have to use palladium and the oxidant. And the third one is alkyne CH activation. Alkynyl CH activation. Here we have to use palladium and a bond state acid. In presence of this, we can form a PMRF complex. So there are the two substitution of forming a PMRF complex rather than this allyl nucleophile. This is called Sujit-Ross reaction. And these are the two substitution of Sujit-Ross reaction, where in absence of leaving group we can also form a PMRF complex. In absence of leaving group we can also form a PMRF complex. So here there is no such leaving group is there, but this is a double bond and there is a CH is available adjacent to this. So this is allylic CH is there, and they have, as a reagent they have used palladium and oxygen. So oxygen is one of the oxidant in nature because we know that it is available, and it can also act as an oxidant. So in presence of palladium and oxidant, it will undergo the allylic CH oxidation. It will undergo the allylic CH oxidation, forming this PMRF complex. Forming this PMRF species. Forming this PMRF species. After that, now there is already a nucleophile in the system. Which is already there. So this OH will attack to this PMRF species, forming a carbon-carbon bond. So it will attack here, and this double bond will shift to this carbon. This will be our desired. This will be our product for this reaction. So what is the correct option? Correct option is option 1. Okay, understood? Let's go to the next question. So the major product form in the following transformation. What will be the major product form in the following transformation? So I have already discussed about carbon-carbon cross-coupling reaction. So there are different type of carbon-carbon cross-coupling reaction. Whenever there is a specific trans metal is using, another metal is using along with palladium, that is called through transmetallation. There are different type of coupling, cross couplings are there, but the type where there is no such transmetallation is used. direct carbon-carbon bond is formed in presence of palladium. That is called Heck coupling. That is called Heck coupling. So here it will go through a Heck coupling reaction. So I just give 1 second, just try to solve, just try to guess which will be the correct answer. I just gave you a hint, it will go through a Heck coupling reaction. Okay. So in case of Heck coupling, what happens first this palladium will be incorporated into this RX bond, that is naphthalene and iodine. Palladium will be incorporated into this RX bond. After that, what will happen? Obviously, it will undergo the 1,2 addition along this double bond. It's only one double bond is available because I have already told in presence of phenyl, all three double bonds are highly stable because of its aromaticity. So it will be taking part, but this alkene can take part. So now it will undergo the 1,2 addition. Now the phenyl group is already below the plane. Phenyl group is already below the plane. So the below the plane is already occupied by this phenyl group. So the approaching this species will approach from this above the plane. So whenever there is electron donating group, whenever, this is a very important thing to remember, whenever there is electron donating group, in this RX species, this R get attached to this alpha position and palladium get attached to this beta position. Okay, so this R will get attached at this alpha position and palladium will get attached from the beta position. Okay, so both of them will get attached from the above the plane because phenyl is already occupying the below the plane. Now it will undergo the reductive elimination. This is oxidative addition followed by 1,2 addition, then reductive elimination. So this now in case of reductive elimination, the metal and the adjacent palladium, the metal and the adjacent hydrogen should be at the same plane to get removed through reductive elimination. Now this palladium is in above the plane. So there are two hydrogen, which is one is above the plane, one is below the plane. But here there is only one hydrogen, that is just below the plane. So this hydrogen can't be involved in this reductive elimination. This hydrogen can't be involved in this reductive elimination. So what will happen? Only then this part of this hydrogen will get removed, will be involved and undergoes a reductive elimination, forming a double bond at this plane, at this side. Okay, so what will be our correct option? Option 1. So the correct option is option 1. Okay. just give 2 seconds, just note it down. So this is going through a heat coupling. First is oxidative addition into the RX bond, followed by 120 addition, then reductive elimination, which is selective to the same plane of the same plane hydrogen adjacent to the metal to undergo a reductive elimination. Let's go to the next question. So in the following reaction sequence, what will be the major product? In the following reaction sequence, what will be the major products Q and R? So they have given para-iodotoluene undergoes all this reagent. So we got a major product P, and followed by iodine and a bromination, they got Q and R. So they have asked for the stereochemistry of Q and R. It will be trans or cis. It will be E or Z. I just give 5 seconds. Just try at least. So what will be the correct answer for this question? So let's go step by step. In case of cross-coupling reaction, if this is silicon, that is called Hiyama coupling. If it is silicon, that is called Hiyama coupling. So silicon is there, and they have also added palladium. So it will undergo a cross-coupling reaction. In case of let's start first this. Still undergoes a cross-coupling reaction to this alkyne, giving this as our product. After that, this is after addition of 1 and 2. So it will just happen, this F minus will, let's go step by step. So first, this palladium will be incorporated into this RX bond. So palladium will be incorporated into this RX bond. After that, when you add this silicon complex along with the fluoride source, that is tributyl ammonium fluoride. So this F minus from the tributyl ammonium fluoride will attach to this plane, and this part will be attached to this R group, and palladium will be removed from the system. So it will form a carbon-carbon bond between this phenyl ring and the alkyne. Okay. Now, in this, if you add 9-BBN, this is the structure of 9-BBN. This is 9-BBN. If you add this boron complex, what will happen? Boron complex always undergoes, I am just denoting this as R. Boron complex always undergoes a C addition, and where the number of hydrogen is less, boron added in that side. So it will be, boron will be added here. And hydrogen will be added to the most in that side. Now, if this is our P, this will be our major product, that is P. Okay. Now they have done two type of reaction. One, they have added iodine. One, they have added bromine. Now it has been seen whenever iodine, I have in one of my videos, maybe in the previous class I have already discussed it. Whenever you add iodine to this type of boron complex, it has been seen iodine just enters at the same site of the boron. Iodine enters at the same place of boron. But in case of bromine, it undergoes a rotation of this bond, and the stereochemistry just reverse, and it added just opposite side of the boron. So the correct option will be option B. So the correct option will be option B. Okay. So here we have learned one new concept, that is this Hiyama coupling, and also that we have recalled another one, that is boron always added syn 2 across the triple bond, that we have already learned in one of our previous classes, that the hydroboration always take place syn across the double bond or the triple bond. After that, if you add iodine, will add it just at the place of boron. But if you add bromine, it will just add it to the reverse side of the boron. That is, if it is cis, the boron complex is cis, then the product will be trans. If the boron complex is trans, the product will be cis. Okay. I hope it's clear. Let's go to the next question. So in the following reaction sequence, the products are P and Q. So they have asked what will be the product P and Q. what will be the product P and Q. Just try, I just give 5 seconds, just try once. As palladium is already there and there is a double bond also, so it will be a coupling reaction. It will be a coupling reaction. Yes, there is no such trans metal, so it will be going through a Higgs coupling. And the next step all knows, I think, is on a reduction reaction. So this we have already discussed, reducing reagents. Just try. Okay, so in the following reaction sequence, what will be the product P and Q? So from the product you can easily, it's visible that it will go through a cross-coupling type of reaction. So first, palladium will be incorporated into this RX bond. Palladium will be incorporated into this RX bond. After that, if you just rotate this single bond, if you just rotate this single bond, this goes here. So it can undergo a coupling reaction between these two carbon, like it will undergo a Higgs coupling. Undergo Higgs coupling. So this R will be added to this plane, as this is a electron withdrawing group. So in case of, as I have already told, if it is electron donating, the R group is attached to the alpha carbon. If it is electron donating, the R group is attached at the alpha carbon, and if it is electron withdrawing, R group is attached to the beta carbon. So adjacent to this, it is a beta carbon. So R group will be attached to this plane, and palladium will be attached here. So PDCN, and their palladium will be attached. Now there is no such hydrogen is available for 1,2 elimination. There is for reductive elimination, there is no such hydrogens are available. So hydrogen will be eliminated from this plane. Hydrogen will be eliminated from this plane. Forming this as our P. This will be our P. So this has been in between A or C. So B are already cut. B and D are already cut. So the product will be between A and C. Now the next is they have added LiLH4. So as we know, acetonitrile, that is the cyano group, can be reduced in presence of lithium aluminum hydride, and it is reduced to CH2NH2. It gets reduced to CH2NH2. So this will give us this as our product. After that it can get reduced to, I'm just drawing this part of the ring because this will be just unaltered. It will be get reduced to form CH2NH2. After that, as they have added IC2O group, acetic anhydride, which will undergo the acetylation. It will undergo the acetylation. So the correct option is option C. Correct option is option C. Okay. Correct option is option C. I hope it's clear. First step is going through a Higgs coupling, followed by a reduction and then acetylation. Let's go to the next question. So before that, we'll just discuss another topic, that is olefin metathesis. So entails redistribution of fragments of alkenes by the scission and regeneration of the carbon-carbon double bond. Because of the relatively simplicity of this olefin metathesis, it often creates fewer undesired byproduct and also hazardous waste than alternative organic reaction. So this is ring closing metathesis. So by this, we can just undergo the addition of these two double bond forming this ring structure. We can also undergo the ring opening metathesis where we can cleave this ring structure to form these two alkene as our product. Now, as our in these cases, as a reagent, the well-established reagents are Graf catalyst. This is a first generation Graf catalyst, and this is the second generation Graf catalyst. The first one synthesized this one, and then the second, this is called second generation Graf catalyst, and these two are called Schoch's catalyst. These are also used for ring closing this metathesis reaction. Graf catalysts are mainly used for ring closing metathesis, and these are for ring opening, but both of them can be applied vice versa. So this is the in general mechanism of olefin metathesis, where so you can see this is the Graf catalyst. It has a metal and CH2 double bond. It is a double bond between metal and CH2. So if you just in generally if you draw it like this, it is about CH2 metal double bond. It undergoes a addition reaction type of with this across this alkene, forming this four member ring, which undergoes a ring cleavage, eliminating this alkene, one of the alkene. Then this will undergoes another addition reaction with the another group of alkene, and through ring cleavage, both the alkene, both this R1 and R2 alkene get attached to itself and forming this ring closing metathesis, forming this metathesis reaction. So based on this type of concept, some questions are coming in this last examination, and it may come to your upcoming examinations. So just to clear it, so this question came in NET 2024 exactly last year. So the major product formed in the following reaction. So as a reagent, they have used Graf's second generation catalyst. So if it is first generation or second generation, the work is same. If there is a double bond, there is multiple double bond, it will undergo the ring closing type of reaction. So let's, can you just try for 1 second or just guess which will be the correct option? So let's solve together. So this Graf's catalyst, second generation Graf's catalyst, if you just draw it in a simpler version, it is like this. Okay. So there is an alkene here. If you start the reaction from here, both are equivalent. Both the double bonds are equivalent. So start from the one side. It will act, if we add this Graf's catalyst across this double bond, this attacks here. So it will form this type of ring structure. I'm not doing this part, we'll draw it later. So it will form this type of ring structure which may undergo a ring cleavage. Forming this alkene species. After that, what will happen? It can again be added across this triple bond, and through similar type of reaction, it will form a ring closing. I am just skipping one of the step. So it will form a bond between this triple bond, and there will be a generation of a new catalytic species, that is this one, which can undergo a similar type of reaction with this adjacent alkene to form this type of ring closing structure. So the correct option is option 4. So the correct option is option 4. Got it? So this is one of the very important topic, because in the same year they have given 2 questions from this type of ring metathesis reaction. So they have given 2 questions from the same concept. From the same concept they just gave 2 questions in the same year, that is June 2024. So from there you can get an idea that is one of the very important concept based on industrial purpose also, because by applying this type of chemistry in industry also, you can form different type of double bonds in just one step. In just by using one simple catalyst, we can form this alkene double bond. So so this is one of the important shock type of catalyst. It can consider as a shock type of catalyst also. So it can also undergo this type of metathesis reaction. So if you just draw it this way, it undergoes a metathesis type. I'm just skip because in the last one I have, this is a similar type of mechanism, just so it will undergo a cross coupling reaction with this adjacent triple bond. And there will be generation of a new species. So in presence of cobalt type of catalyst, alkyne and alkene undergoes this type of cross coupling reaction, generating alkene bond here. After that, as carbonyl is already there, in presence of carbonyl, there will be incorporation of carbonyl group here, and it will form this as our product. We form this as our product. Okay. So the correct option is option 4. Correct option is option 4. So next question is what will be the major product formed in the following reaction? So this is based on another different type of transition metal, that is iron. So iron efficiency can be acts as a very good Lewis acid. So it can coordinate with this oxygen in enhancing the electrophilicity of this carbon. So because it can open up and there will be generation of positive charge here and can act as electrophile, and there is a internal nucleophile. This in double bond is there, so it may attack to this plane. So let's go step by step. See, it opens up, so it will form now. As this is above the plane, so that nucleophile should approach from the below the plane, so it will approach from the below the plane and it will open up. Next, as it is approaching from the below the plane, there will be generation of positive charge here, so this will also approach from the below the plane here. Now there is generation of positive charge here. This will then, and this, as these two two alkyl groups are showing that they are above the plane. They are just tilted above the plane. So the approaching nucleophile is coming from the below the plane. In this case also this is showing this is above the plane. So these OH will come also from the below the plane. So it will be the consecutive attack leading us this type of cyclic thing, tetracyclic thing. Okay, so the correct option is, so these two methyl are above the plane and this OH is also above the plane. So you have to find where the two methyl are above the plane. So here one is above the plane, so but this is below the plane, above the plane, above the plane, above the plane. But here you can, from the structure you can see there is a proton which is below the plane. So this is not possible. Is above the plane is not possible. This is not possible. This is also not possible. So here it is above the plane, above the plane, above the plane. The hydrogen is below the plane. So the correct option is option 3. Correct option is option 3. Okay. Let's go to the next question. Before that, there is another topic which we will discuss, that is called Walker oxidation. The aerobic oxidation of ethylene to acetaldehyde in presence of catalytic aqueous palladium chloride and copper chloride, that is called Walker oxidation. It has a huge application in industry also, where we can easily form acetaldehyde just from an alkene. You can easily form acetaldehyde just from an alkene. So based on that also one question came in one of the previous year. So they have given this type of alkene substituted cyclic ketone and they have added this reagent. Whenever you see palladium chloride, copper chloride and oxygen, that is simply a Walker oxidation. Simply a Walker, palladium, copper and oxygen, that means this is a Walker type of oxidation. So in presence of Walker oxidation, what happens? This alkyl undergoes oxidation forming this acetaldehyde. So this part will transfer to acetaldehyde. So here the acetaldehyde is only, there will be a ketone formation here. So the correct option is A and B is not possible. So it will be between C or D, because this will be outward. There will be carbonyl center here. There will be generation of carbonyl bond here. Now the second step, they have added acid. So if you take this one, if we add acid, what will happen? So there is a proton that is acidic. So this can goes here. In presence of H plus, it is acid. This OH get coordinated. So this can attack to this carbon center, forming this there will be a OH. After that, just to get a stability, it will undergoes a elimination of water, generating this as our product. So the correct option is option D. Correct option is option D. Let's go to the next question. So in the following reaction sequence, the products P and Q. So I have there are various type of transition metal. So among them copper is one of them also. So this CH3CU, this is called a Gilman catalyst. This is called Gilman catalyst. In presence of Gilman catalyst, whenever there is alpha beta unsaturated ketone is there, it specifically attacks to this beta carbon and it goes here. So this negative charge can again attack to this selenium and remove this bromine from the system, generating this as our P, generating this as our P. In presence of H2O2, this undergoes a oxidation, selenium undergoes a oxidation, forming selenium oxide, which may undergo a 1:2 elimination. So this comes here and selenium gets removed from the system. So the correct option is generating this as our product. So the correct option is option B. Correct option is option B. I hope it's clear. So there's another question. This is last maybe. So I have already told you about the phosphorus chemistry. So this is based on that. Just to recap things which I have already talked. So phosphorus can be used. I have already talked about Mitsunobu reaction. If you remember, in case Mitsunobu reaction, what happens in case of Mitsunobu? It's dead PPS3. The reagent is PPS3 and diethyl azodine carboxylate. So what happens in dead PPS3 attack to this OH and it makes it is a good living group. Similar type of reaction will happen in this case also. So this PPS3 will attack to this CN and generate selenium hydroxide. After that, what will happen? So it will generate this selenium nucleophile. Again, another PPS3. Then again, now this OH, now this has been formed, this PBO3 plus and Cn minus. So this has been formed in our as our byproduct. This has been formed as a byproduct. So what will happen now? So this OH will attack to this phosphorus and Cn will be removed. We know that oxygen phosphorus is one of the strongest bond in organic chemistry. So whenever there is oxygen and phosphorus, it will always make a bond between them. So it will form this type of species. into them. Selenium will attack to this carbon center and remove this from the system. So the product will be 4. Okay. So here first phosphorus is acting as a nucleophile to remove the CN from the system and generating selenium, a new nucleophile, that is selenium minus. Again, OH is acting as a nucleophile and attacking to the phosphorus, turning OH to a good leaving group. Now the selenium nucleophile will again attack to the carbon and remove the oxygen phosphorus complex from the system and generating this type of species, by this process we can easily form a carbon selenium bond in nature, in our lab. So in this way we can form a carbon selenium bond in our lab. So thank you everyone. So I just give a quick recap of whatever we have discussed today. So we have discussed mainly about the cross-coupling reaction. Then we discussed about different type of cross-coupling reaction and their general mechanism, followed by the use of palladium in hydrogenation. Then we solved some question based on this type of cross-coupling reaction. We have also learned about Sujitro's reaction and also the substitution of that is allylic CH oxidation and allylic CH and alkynyl CH oxidation. We have also discussed about this different type of previous year question based on Hake, Hiyama, another Hake type of reaction. We have also discussed about olefin metathesis and some question based on that. Then the use of other transition metal in case of organic reaction. We discussed about Walker oxidation and some other examples of that. So thank you everyone. I hope you have enjoyed this class and it may help you to solve the upcoming examinations and your assignments. So let's meet in the next class. Have a nice day.